Okay, so welcome back to the second half of semester B. This week I want to discuss first order logic. So we previously studied propositional logic, which hopefully has been relatively easy. And remember, we studied it by splitting the ideas into the grammar, the proof theory, the model theory, and the meta logic. Now, it may have appeared in that lecture that we were going into a lot of detail about something that is a relatively simple logic, and thinking about all these categories may appear a bit like overkill at times. But the reason we've done that is because when we come to first order logic now, those concepts will carry over. And it is a good introduction to have seen these concepts used in propositional logic before they show up here. So as a reminder from last time, the grammar of the logic, otherwise known as the syntax, is purely about strings. It's saying what makes up a formula in the logic. What are the symbols and how are they combined together? When we go to proof theory, we are now doing logic. We are now looking at rules which can take one or more theorems as inputs and produce the theorem as a conclusion from them. So grammar is about creating formulas. The formula has no concept of whether it's been proved, whether it's true, anything like that. A formula is just a string, a text. Whereas when you go to proof theory, you are now saying some of those formulas are special and they are called theorems. And a theorem is anything that can be proved using the rules of your logic's proof theory. When we go to model theory, we are talking about truth rather than provability. Proof theory is about provability. Model theory is about truth. Whether or not a formula means something, where meaning is defined through a structure which maps a formula of your logic to something else, to something in the real world, or to something in mathematics, or to something in Boolean logic, as we saw last week. And then the meta logic is doing logic about logic. It's looking at the logic from the outside and trying to figure out what it's capable of, and often more importantly, what it isn't capable of. What are the limitations of the logic? So we're going to go through the same 4 stages again, but this time it's more complicated because we're doing first order logic. So hopefully you have all seen first order logic before. When you studied probably AI, you'll have seen this show up in the form of prologue. Hopefully you've seen some of the underlying logic that goes into prologue as well. Just a recap on what this is then, and how this is different from what we saw last week. So last week we discussed propositional logics. And propositional logics are logics about facts. Remember, we looked at expressions like this. This is x and y. And we talked last time about what x and y are typically used to represent. And the point is that x and y are representing facts about the world. So this expression here, x and y, could be intended to mean something like this. It could be intended to mean something like snow is white and this apple is red, where x is meaning snow is white and y is meaning this apple is red. What you notice then is that in propositional logic, we can only talk about facts. But when you look at these facts, snow being white and apples being red, or being red, you can see that. Hello? Hello? Was that a question? Was that a question coming in? No? Okay.
No, I don't think so. I think your microphone.
Someone has a microphone on. Okay.
Yeah, your microphone sort of like made a little noise, and now your video is not showing. Well, no video showing actually for anyone. I don't think.
Okay, can you still hear me?
Oh, I can hear you, but apparently my connection is bad.
Ah, okay.
Hello.
Okay, when we look at the English translations of these intended meanings, you can see there is actually more structure within these concepts. So snow being white seems to include at least two substructures. There's the concept of snow and there's the concept of white or whiteness. And here we have the concept of this apple and the concept of red. And notice the difference between these two facts. What's the difference in form between saying snow is white and this apple is red?
This apple refers to a specific thing, where snow is more the general. It encompasses all things that are snow, whereas this apple refers to specifically.
Yeah, absolutely. So this really means all snow is white, whereas this means this one particular apple is red. So in propositional logic, all that is hidden away. It's not represented in the logic itself. It's part of the interpretation. But sometimes we would like to be able to represent that substructure in more detail. And so first order logic is one example of what are called predicate logics. The name of first order logic suggests that there may be a second order logic and higher order logics, which in fact there are, but we're only going to talk about first order logic in here. So predicate logics in general are logics where you can say things about substances. So the word predicate, I believe, comes from Aristotle, from Greek. The word predicate is a verb and it is a noun as well. Interestingly, it's the same word, but we pronounce it differently depending on what it is. If it's a verb, we normally say predicate, as in I'm going to predicate something of this apple. I'm going to predicate the fact that it's red. And it means to say. I'm going to say something about the apple. So that comes from Aristotle and Greek. So predicate means to say something, usually to say something about something else, like saying that the apple is red. When you use it as a noun, we would normally pronounce it predicate, written the same, pronounced differently. In that case, we would say that red is a predicate, possibly predicate, depending on your accent, I guess. So here red is a predicate. We are applying it to apple, and therefore we are predicating it. We are predicating the redness of the apple, and all that means from the Greek is that we are saying something of the apple. We are saying that it is red. Okay, that's all it means. So in predicate logic, then, we're going to make a distinction between substances and predicates. And roughly a substance is what in English, everyday English, you might refer to as a thing or a physical thing. Not necessarily physical, but it is a single specific substance which exists and things can be said about it. Whereas a predicate is what you are saying about a substance. So the apple one is a substance, and the fact that it's red, we are saying it, it's a predicate. So there's still a bit of cheating going on here. By giving a name to this substance as apple one, you're kind of cheating by implying a whole load of appleness about this substance, which only English speakers would get from the name. So in really formal logic, you probably just want to call that substance something like substance one. You have a whole bunch of substance one, substance two, substance three, and you could say several things about substance one. First of all, you could predicate that it is an apple. You could say, is apple bracket substance one, to predicate its appleness about it. And then you could predicate its redness about it by saying red brackets apple one, red substance one, close bracket. So as we mentioned, there's a difference between these general statements like all snow is white and specific statements this particular substance is red. So here we are predicating the redness of substance 1, which is a specific instance. What we're doing here is saying all snow is white. So has everyone seen, we should all have seen the upside down A's and the backwards E's before by now. Remember, upside down A means for all, and backwards E means there exists. So this is saying for all substances X, snowness of X, well, X being snow, implies whiteness of X. So it's saying if X happens to be snow, then it is also going to be white. Okay? Snow of X implies whiteness of X. So if you can say that X is snow, then you can also say that X is white. So hopefully this is familiar and is revision. You see the big difference is that in propositional logic, X and Y are facts. So X and Y can be true or false when you go to the model theory. But in propositional logic, we're using those symbols differently. Here, X, and if we had a Y as well, X and Y are not facts. They're not things that can be considered true or false. X and Y instead are referring to substances. And the only things that are going to be true or false are predicates said about substances. So in propositional logic, you can say X is true. In predicate logic, you can't say X is true because X is just a substance, but you could say A of X is true, where A is your favorite predicate. Snow of X could be true. So in first order logic, that was a simple example of a formula written in first order logic. We can define all the available formulas using a grammar as we did for propositional logic. And this is hopefully going to look very familiar because it's almost the same as the propositional logic grammar, but it includes a couple of extra components. So for first order logic, we can consider variables and predicates. So a variable, there are slightly different ways of setting this up. In this definition, a variable is a string that is composed of one or more lowercase letters. Okay, so in some cases we might allow numbers, in other cases we might allow uppercase letters or other things. But in this particular setup, we're only allowing lowercase strings. Question from Matthew.
Sorry, just to be like exactly exact, a variable maps one-to-one with a substance. So a variable represents a substance directly.
In some cases, let's be very careful about this. Yeah. Yeah, okay, in some cases it's going to refer to one particular substance, and in other cases it is it's floating. So here, for example, X is a variable, but in this case it is referring to a particular substance. So
Okay.
I guess if you really wanted to, in this grammar, you could say something like for all apple, P of apple, you're allowed to use a string as your variable being quantified over in this case.
Okay.
Okay. Yeah. Again, there's slightly different ways you can set this up. Yeah. If you're actually going to implement this, you might want to separate out those two cases in your grammar. You could have substance name and quantify variable as separate terms. But yeah, good question. Very good question. Okay, so then we will include predicates as well. And in this case, to make it obvious what's a predicate and what's a variable, we'll say predicates have to be written in capital letters. So you're allowed to say things like, for all x and y, parent of x and y. So here, parent of is a predicate taking 2 arguments in this case. Question from Fionn. Question from Fionn. I see a raised hand from Fionn. No? Okay. Okay, once we have variables and predicates, then we can then go to expressions, otherwise known as formulas. So expression is a word that comes from language design. Formulas is a word that comes from logic. In this case, they're the same thing. So if you're an expression, we've got the usual things we've seen from propositional logic. So an expression can be, well, in this case, you can't just have x as an expression. You have to say something about it. So you can have a predicate of a variable as your basic expression. But then inherited from propositional logic, we've got these combinations. We can say something and something else, something or something else. We can negate it. We can put in implication. But we can also make these constructions where we introduce what are called the quantifiers for all and exists. We can now make an expression that says for all, yeah, there's your variable again. Yeah, so if you wanted to set up the grammar where that kind of variable has a different, what's the word? What are these things called? It has a different name within the grammar, yeah? Different type of grammatical entity. Yeah, here you can now say for all x, some expression is true of x, or there exists an x, so that the expression becomes true. So that's the abstract definition. Sometimes it's easier to understand just by looking at some examples that are composed from grammar. And I'm being as accurate as I can with the brackets again in this one. So you remember last week we were very careful with the brackets, and then we discussed that you can add what is called syntactic sugar to simplify the way things are presented to humans. But using this formal structure of the grammar, we're going to end up with a lot of brackets. So for example, we can generate this thing. This says, does anyone want to translate this into English? Anyone want to have a go? So there exists a.
There exists. There is an a. Such that. For all d.
Yeah.
It's hard how would you pronounce this? Would you say the predicate r, or would you say the function r, such that r of a?
Yeah, you could say r of a. Yeah.
R of a and s of b.
Yeah.
Or.
Yeah.
Not. There is an element c.
Yeah. Well, how else would we translate that? How would you translate this whole thing together? You could say there isn't an element c.
Oh, there is not an element c. So that applies there, but there's a bracket between them. So I would have said that actually.
That's not quite correct then, is it? Yeah, you'll have to say something like, it is not the case that.
Or there is not. It is not the case that there is an element c. Okay, that's good. There's an element c such that r of c. Oh God! Now, how would you pronounce this with the brackets? So that's actually does apply directly to element. So you could actually, I think, say there is not an element c, because the closing bracket terminates after the e.
Yeah. Okay. So we can actually say it is not the case. So we can say there isn't a c such that r of c. Yeah. and S of D. Okay. This is why we have the logical notation, because it's actually easier than trying to read it in English.
God.
You have to make little
Yeah.
pauses in English to try and suggest where the brackets might be. Okay, good. Yeah, many political disagreements could probably be resolved if they were all done in formal logic. You'd see where the disagreements actually were for a start. Okay, so how about this one? This one's got some readable names on the predicates. So it's for all x, for all y, parent of xy implies child of yx. Okay, and what does that actually mean? What are we trying to say if we make this claim in logic?
He's saying that if something is a parent of someone, then that means the child y is also the child of that parent. It's the association between the parent and the child is affirming that.
Good. Yeah, it's saying if someone is your parent, then you are their child, roughly. Yeah. Okay.
It reminds me a lot of prologue syntax now.
Yeah, so prologue is based on first order logic, so a lot of these concepts go straight into the prologue language. Okay, good. So how about this last one? How do we read it, and then what does it mean again?
So would this one just be for every case of x such that there exists y, where x is the parent of y?
Okay, so for every x, so if the substances are people, for example, we're saying for every person x, there is some other person y, such that x is the parent of y. Okay, so what does that actually mean? Who has children and who has parents, if this is true? I think this is saying if everyone is a parent. Yeah, it's saying for every person there is someone who they are the parent of. So it's saying everyone has a child. Yeah.
Therefore, it is false.
In the particular world that we live in.
It also depends on how we define this parent of predicate, because if we actually open up the predicate, it might actually say that y is the parent.
Yeah. Okay. So again, you've got to be really careful because this is an English word, and it's always the reason that classic AI failed was basically that people used English names for all these things, and they implicitly assumed that those words had a lot more meaning than they actually have in the logic. Yeah, if you go around throwing around this variable called parent of, everyone who looks at it, who's a human, thinks it has all this implied semantics about parenthood, and it doesn't. It's just a string of symbols that has to be defined inside the logic. So yeah, we'll talk soon about how we make those definitions more rigid in the interpretation. So yeah, in practice, you will add a bunch of syntactic sugar to this. So in particular, you notice there are no functions here. You might want to define a function. If the substances are numbers rather than people, let's say you want to talk about things like 3 + 2 = 5. This should be something we can express. And this addition is what you normally think of as a function. You can write this as a relation just as well. If you define addition now as a relation which has 3 inputs, you take 3 and 2 and 5, and you can use this type of sugar just to think of everything as being a relation, because a function is just a kind of relation. Okay. So yeah, the main thing to remember is you can't say x and y anymore, because x and y now refer to substances, and substances don't have a truth value. Only predicates about substances have truth values. So you can say snow is white and this apple is red, but you can't say snow and apple that doesn't mean anything. As with the lambda calculus, we have to consider bound and free variables. So this should be very familiar from lambda calculus. In these examples, we have everything is bound. You can see all the variable names are showing up in the quantifiers around the edge. Okay. And again, this maybe helps to answer Matthew's question. You know, one way to read these is to assume that anything that isn't bound is referring to an individual rather than being used as a variable. So if we write something like this has a free variable x sitting in it. So you might interpret x as referring to a particular individual substance in that case. Or another way to interpret this is as just allowing x to range freely. If you do allow x to range completely freely, you will notice that the sentence then doesn't have a truth value anymore. You know, is it true or false that there exists someone so that x is their parent? And if the answer to that is it depends. It depends who you mean by x. That's called a contingency if you read it in that way. So here's an example of a four-place predicate. This is called kills at location with weapon. So this is like Professor Plum kills Colonel Mustard in the study with the candlestick. That's a predicate with 4 inputs. That's quite a complex relation between those 4 substances. So you can see roughly in English, predicates are a mixture of properties and verbs. Now, if you say red X, you're saying something about X. You're saying it has this property of being red. If you say kills at location with weapon, you know, this is a verb taking 4 arguments. And in some languages like Latin, you would what's the word? Declench. You would have different declensions of each of those nouns. If Professor Plum kills Colonel Mustard, Professor Plum is the person who's doing the verb. Colonel Mustard is the object of the verb. The library is the location, and the candlestick is the object being used to do the killing. And in Latin, I think you would put a different ending on each of those nouns to indicate which of the 4 places they're sitting inside the predicate. There's a little bit of it left in English, just now and again. If you say, for whom the bell tolls, you're using whom as the object rather than the subject. I think the bell is the subject and whom is the object, which is why you put the letter W on it, because it's left over from ancient German or something and landed up in English. Okay, so that is the basic grammar of first order logic. Hopefully we've seen all this before, underlying systems like Prolog. Now let's take a look at the proof theory. As with the grammar, the proof theory is going to extend what we've already done in propositional logic. So this should all be familiar from last week because it's just a copy of the same slide. There's some different text up here. So all you have to do to make the old rules work is just remember that phi and psi now aren't variables, they are predicated facts. So if you're going to say snow is red and the sky is blue, you can consider phi and psi as referring to the redness of the snow and the blueness of the sky. But they're going to be applied predicates looking like this: A of x, B of y. So remember from last week, this notation means if you're allowed to say phi and you're also allowed to say psi, you are then allowed to write this string. You're allowed to say phi and psi. And the stuff going on up above the line is semantic. This is saying you have been able to prove this. Also, you have been able to prove this. And you are therefore allowed to write this down and add it to your collection of theorems. So in the bottom line, that and is just a symbol. It's a symbol in a string in the new theorem you're making. Whereas the fact that things are written on the left and the right above the line is a semantic thing. That's saying that you've proved phi and you've proved psi. You've proved two things and you're allowed to write the thing underneath the line as well. So these other rules are just the same, right up to implication. So if you've proved phi and you've proved that phi implies psi, you are then allowed to write down psi, for example. In first order logic, we are going to add some extra rules so that we can do proofs containing the new symbols, including the quantifiers, upside down A and backwards E, but also including equality. So in propositional logic, there's no concept of X equals X, because in propositional logic, it's just a fact. Snow is white. You can't say snow is white equals snow is white. Because snow is white isn't a thing, it's a fact. Whereas in first order logic, you can discuss equality. You can say this apple equals your apple. That would be a proof of who owns this apple. It's you. So we have to introduce an axiom to explain what is equality. And for some people, this is taken as the very foundation of the whole of Western philosophy, I think. Ayn Rand has this as one of the titles of her chapters, which she's taken straight from Aristotle as the beginning of everything. X equals X. Basic axiom of logic, which some of the philosophers have probably found ways to argue with, but we're going to take it as an axiom. So this introduces the concept of equality, two things being equal. We've then got to provide rules for allness and existness. So we'll do the elimination ones first for these. Remember, every rule has an introduction and an elimination. Introduction means if you didn't have a symbol above the line, you get it below the line. Elimination means if you have the symbol above the line, you can get rid of it below the line. So elimination of for all, this says that if for all x, phi is true, you can also have a theorem where you write down phi, but you replace the variable x with a particular instance t. So remember, this reads as phi with t substituted for x. So if you've proved that phi is true for all x, then you're allowed to write down phi being true for one particular value of x. Existence goes the other way around. In existence, if you've proved that phi is true for one particular value of x, t, you are then allowed to write down there exists at least one x that makes phi true. So what would be an example of that then? This first one is all apples are red, therefore this apple is red. Whereas for elimination, for existence, you start with this apple is red, and you conclude there exists at least one apple which is red. There's an old joke about the social scientist and the philosopher and the physicist or something on a train in Wales, and they look out of the train window and the sociologist says, look, all the sheep in Wales are white. And the physicist looks out of the window and says, no, there exists some sheep in Wales which are white. And the philosopher is even more accurate, and they say, no, there exists at least one sheep in Wales, at least one side of which is white. So determining what you can imply from a particular observation. So let's look at the flip side of each of these rules now. The flip sides are a little harder to understand, but let's see what we can do. Here we are eliminating the equality symbol. So we've started with terms including equality and we're getting rid of them. So here we're saying if you have two things that are equal, if T1 equals T2 and phi is true of T1, then you may conclude that phi is also true of T2. So for example, if this apple equals your apple and this apple is red, then I can conclude that your apple is red. This is the introduction rule for upside down A. Now you remember this concept of a fresh variable? We saw this in the lambda calculus lecture. A fresh variable is one that doesn't have any baggage. We haven't proved anything about it before. We haven't used it. This says if you could pick a fresh variable called t and prove that phi is true of it, then you're allowed to say that phi is true for all x, because it doesn't matter which one you picked. T could have been anything. And so you can conclude that the thing is true for everything. And then here we're going to eliminate exists backwards e. So in this case we're saying if there exists an x such that phi and t is the fresh variable and phi proves chi, then you're allowed to conclude chi. So this is the standard way of getting rid of a existence statement. So all the same stuff we saw last week in propositional logic, together with some new rules for introducing and eliminating quantifiers, upside down A and backwards E. I'm going to ask you in a bit to try doing some example proofs using these rules. Hopefully you've all read the chapter from Huth that I put up as reading for this week. This is one of the proofs from that chapter. So you can see here we've started with something and we're going to go through applying different rules. These are the names of the rules that we've just seen. It's telling you which rule has been applied at which step. In this notation, the boxes mean assumptions. This is a slightly different notation from what we've used, but this is what Huth does. So you can see if we're allowed to write that down, we're going to apply one of these rules. In this case, we're making an assumption. So remember, you can assume whatever you want in an assumption. So let's assume that that thing is the case. There we're going to make another assumption. Under those assumptions, you can then conclude some more stuff. Down here, we're applying identity, we're applying another rule. And then by the laws of probably implication, you can get rid of those assumptions and pop back to what is actually the case. So here you've started with a premise, and you're going to show that if that premise was provable, then this conclusion is also provable. Now this notation, this is called Fitch notation. It's slightly different from the way we've notated our syllogisms. You can roughly imagine just drawing a line in between each of these statements. You're just concluding something from the line above it. You'll also see this notation show up in Gödel-Escherbach. It's Hofstadter's favorite notation. And you will see it looks a little more like a program. There's this concept that each line has a number, and at each line of the proof, we are invoking one of the rules, and we're writing down the current state of the system, the current theorem that we've managed to prove. So when your proofs get bigger, it's often easier to switch to this notation, so you're not writing down these enormous trees of syllogisms. When we get to verification, you'll see how quickly those trees can get very big. So it's easier to write things in this more linear, line-numbered fashion. Now, when you try and do this, remember the history of logic, right? There used to be grammar and logic and rhetoric, and grammar was syntax in ontology, and logic was the study of arguments that already exist. Okay, if I give you this argument, this proof, and ask you to check it and explain it, that's what was traditionally called logic. So I'm going to give you a bunch of these from Huth to read and check doing logic. Going beyond that, there are other questions in Huth where you are asked to create a proof. So that's what traditionally was called rhetoric. You're inventing a proof for yourself. Now, this is where first order logic is very different from propositional logic, because in propositional logic, it's very easy to do that. And in fact, there are algorithms that tell you what to do. You will find in first order logic, it is often not obvious how to go about creating a proof. Okay, if I give you that premise and I say, can we get to this? You know, this is like the MU system. You know, I gave you, what did we start with? MI, I think we started with. And you were trying to get to MU by applying the rules of proof. You know, you now have a puzzle to solve. You have a creative task to figure out what order to go out and apply all the rules to get from the starting point to the finishing point. And you know, when you see people talk about human creativity, the next question is always, is there a way to do this using AI? How do we automate that creative process? And there has been a lot of debate, and continues to be a lot of debate, about how much of this requires a human and how much can actually be automated. Shall we take 10 minutes to get a cup of tea, and then we'll come back and do the model theory at 3 o'clock? Any questions before we go?
Nope.
Okay, let's get a cup of tea. I don't know if we're going to make it to the meta logic today. Maybe save it till next week. But let's come back at 3 and we'll look at the model theory. See you in 10 minutes. Bye for now.
Cheers. Hello.
Welcome back. Still there?
Hello.
Hello. Right. As I said, I'm not sure how far we're going to get today. Would you guys prefer to listen to me talk for 3 hours again, or would you rather stop early and potentially not have as much content in the module, but spend some time actually doing logic exercises in the class?
Both of these sound optimal. I don't.
I know I may have killed people a little bit last time by talking for 3 hours, but on the other hand, we are recording them, so you can always fall asleep and then watch it on the replay another day. Let's see how we get on. Let's do the model theory first, then we'll think about the meta logic. The meta logic is where this gets fun. That's where the famous Gödel's theorem comes in. But before we get to that, we need to do the model theory. So remember, for propositional logic, the model theory was Boolean algebra. This is about assigning meaning to formulas. In particular, creating a structure which maps a formula to an interpretation. And then a model is an interpretation that is true. So for Boolean algebra, we saw a way to do this by setting up the truth tables, the same truth tables that we see in digital logic, and recursively combining them together. And ultimately, they end up assigning a truth value to your formula. Now, when we go to first order logic, it's more complicated because we're potentially dealing with unlimited sets of substances. If you say for all x, x is red, it may be difficult to figure out whether or not this is actually true. And for starters, it depends which structure you are using. If x, or rather if the quantifier, if this symbol for all is supposed to mean ranging over the 3 people in this room, then we're going to read the sentence as for all the 3 people in this room, they are red. Yeah, or for all cars in this car park, the car is red. That kind of thing is quite easy to check, because you can go and look at each car one at a time, and there's a limited number of them, and when you're done, you can tell whether or not the thing is true. However, if you're dealing with an unlimited set of substances, such as numbers, or I don't know, all the people in the world who've ever lived and ever will live, people in general. If you're saying all people are red, that's going to be harder for you to figure out, because you can't just go and look at each one one at a time. So when we talk about choosing a structure, we're talking about what is the domain, what are these substances actually going to be, how many of them are there, and what kind of relations are going to exist between them. And the structure we choose depends on what we're doing. So in particular, there are 3 major uses of logic in computer science. It shows up in AI, it shows up in verification, proving that programs actually work, and it shows up in mathematics, if you want to apply computer science to pure mathematics. So each of those 3 domains will be using completely different structures, which give different interpretations to your formulas. So X here, X, if you're doing AI, X could well mean something like a car, or all the cars in a car park. X is usually going to mean, in its most general, X is going to mean all substances in the real world that you might want to talk about. You might say substance 1 has appleness and substance 2 has carness, and there's a relation between substance 1 and substance 2 that the apple is in the car, that kind of thing. Which is roughly what you find in a system like Prolog. If you're doing verification, X is usually going to represent something like the state that your program is in. And you're going to say, for all possible states my program could be in, does some property hold, such as not crashing is the usual one. And if you're doing applied computer science for building pure mathematics, then X is usually going to be a number of some form, you know, a natural number or an integer or a real number, whatever. So when you choose a structure, then you're going to choose: are we going to have a finite set of substances, or are we going to have unlimited substances? And when you have unlimited substances, we talked before about the different sizes of infinity. Usually when we say unlimited substances, we mean this notion of countable infinite substances, which means, if you remember, it means that you can match up each substance with a natural number. So you can say this is substance 1, this is substance 2, this is substance 3. You know, there are some sets of things which are bigger than that, and you can't make that mapping to the natural numbers. So once you've chosen your substances, then you're going to go and choose your relations, you know, otherwise known as predicates. For some reason, when we get to the model theory, they're normally called relations. They're predicates in the proof theory. You know, a relation is not a syntactic concept. It's the actual, often physical relation. You know, if you say the apple is in the car, that relation is true if in the physical world there is an apple and a car, and the apple is in fact in the car. And that assigns a truth value. Remember, that's distinct from a provability value from the proof theory, because here we're doing the model theory. So predicates, relations that only have one argument, are often viewed as being properties. You know, red is a predicate with a single argument, or it's a relation only applying to X. You know, two relations are things like father. You know, substance 4 is the father of substance 5. Or you can have relations with more arguments. So we talked, for example, about mathematical relations. You could have a relation called is sum. You know, this is a way of expressing the idea of addition. You're saying, is it true or false that this relationship holds between the numbers 2, 3, and 5? You know, this is true if 2 plus 3 actually does equal 5, and otherwise it's false. So to create an interpretation, then you're going to make a choice of which relations are actually true. You know, either if the car actually does contain the apple, that's an interpretation. It's a possible world. The apple really is in the car, and under that interpretation, the sentence "apple is in car" is going to come out true. So in some cases, you have a lot of choice about what interpretation to use. In others, you don't, and we'll see that in a moment. Just as with the propositional structures we saw, the Boolean algebra structures, we can define a model to be any interpretation which makes a formula come out true rather than false. So the physical reality where there's a car and there's an apple inside it, that world is a model for the sentence "the apple is in the car," because it's an interpretation which assigns a value of true to the formula. If you choose a world where the apple is not in the car, that is an interpretation, but it is not a model because the formula comes out false under that interpretation. A tautology is a formula where every interpretation is a model. Whereas an inconsistency is the opposite. This is a formula where there are no models. It's just impossible to satisfy. So if you have a formula, something like A of X and not A of X, that creates an inconsistency because there's no possible model of anything that is able to satisfy that. And you might consider contingencies if there are some free variables in your formula, and you actually want to interpret them as free variables rather than names of substances. So you know, for all X, Y is the parent of X. That formula might be true or it might be false because we haven't said what Y is. So you can come up with some interpretations where you choose a Y to make it true and some where it comes out false. That's called a contingency. So if you have a finite structure, you've got a finite number of these substances and relations between them, then it's very easy to check for tautologies, because you can just try out every interpretation, of which there are a finite number, and you find out if they're all true. And then you have a tautology. If your structure is infinite, then it is not always impossible, but at least harder to decide whether something is true or false. You know, for all x is red, where x is people, and there's an unlimited number of people. You can't go around checking each one to find out if it's true or not. Let's make this a little more concrete. That was quite an abstract overview. Let's talk about these three use cases: AI, verification, and maths. If we are doing AI, we will usually choose this type of structure. In this notation, the white circles are substances and the black circles are relations. So in this case, we've got a bunch of substances which I've labeled as A, B, C, D, E, and so on. Usually we consider that there's an unlimited number of them. We're only ever going to talk about a finite number of them, but if we ever need another one, we can go and create a new letter and use that as a label. And these are actual stuff in the world. You know, A is an actual thing. Now, depending on your philosophical view, this is either a thing in the actual real world, or it is a thing in your head, in your phenomenal world. And the philosophers can get very excited about this. Does the actual real world consist of substances and properties, or are those things only invented in our heads? From our point of view, it doesn't matter so much today. So we're going to assume that we have some world which contains a bunch of substances and a bunch of relations. So, you know, for example, what's going on here? Can anyone describe what's happening in this interpretation?
So this is a description of someone and their relations to the things that they own and their parents. So you have a man who's mortal, whose father is B, and their mother is E. They have a gun, which is G, and they killed their mother.
Okay, good. Excellent. It depends which way around you want to read the father and mother relationships, right? A could be the father of B, or vice versa.
Yeah, I was going to say it.
How you set that up. Okay, good. So this interpretation is one interpretation from a structure, and the structure is the set of all the interpretations that we're going to consider in AI. So you know, we didn't have to have A being the father of B. You know, A might have been the father of C. That would be a different interpretation. But yeah, excellent. So this interpretation is describing a murder, basically. It's the backstory for a murder investigation. So a couple of things to notice. See how the relations are notated, right? This is a relation corresponding to a single place predicate. The mortality of X is a predicate which only involves X. So it's notated by a line, you see? Whereas fatherhood is a two-place relation corresponding to a two-place syntactic predicate. So you can see the father relation has got two lines coming out, and one end's got an arrowhead on it and one end hasn't. So the end that doesn't have an arrowhead is the same line we used before. That's showing the first argument of the predicate, if you like. And the arrowhead I'm using to mean the second argument. And if we go to a three-place predicate, so kills, you see the first input is A. So I'm assuming that means the subject of the verb. I think the second one is shown by the arrowhead. So that means the object of the verb. And the third one I've done with a little dot on the end. You can see there's a different kind of arrowhead. That's to show that it's the third place in the predicate. Which, do we have any Latin speakers in here? No? Any other language speakers? Possibly that's called a dative or a transitive or something. It means it's the thing that is used to do the killing. Right? So A is the subject who is doing the killing. E is the object who is being killed, and G is the instrument that is used to do the killing. So you might want to turn kills into a four-place relation with another kind of arrowhead. Maybe you have one with a square, and you could say, in the library, and that would be a locative input to the relation.
Would it be like a valid way to say if you had E, which was property, well not property, but like a substance of killed by, and then the relation from A and G, would that still be valid? It's just a valid way to say that, or?
Yeah, so you could always swap these things around. Saying that A is B's parent is the same thing as saying B is A's child. Yeah, you can define a relation either way around. Even with things like arithmetic, the fact that 2 + 3 = 5. When you look at it as a relation, it's just a relation connecting three things together, right? It's got three inputs, 2, 3, and 5. And that relation is actually expressing the same fact that 5 - 3 = 2, or that 5 - 2 = 3. So yeah, you can always spin the things around and imagine different things as subjects and objects. And if you read Frege, he gets very excited and worried about this. And it's possibly one of the reasons, again, why classical AI still doesn't really work, because again, to a human, you can look at parent A, B, and you know that means that child B of A, but the machine a priori doesn't know that. It doesn't know how to flip the relations around unless you specifically tell it that. So AI is a nice application of logic because the structures are nice and easy to understand. You can see the substances are actual substances. By the way, the word actual has a precise philosophical definition. Right? Something which is actual means that it exists in the world that you are in, and it is the opposite of hypothetical. Maybe you can imagine a possible world where X is not the case, but the world you're in, the actual world, X is the case. So when you hear teenagers throwing the word actually around, yeah, that's like my actual thing, there is some content in the word actual. It means the world that you are in. And when we say we're talking about actual substances, we mean substances that are in this world, not things that are just mathematically made up entities. And that's the whole point of model theory. It's making a mapping from the syntactic structures to stuff that is in the actual world that we are in, so that we can talk about it. Okay, let's look at a different structure of interpretations and consider the case of doing verification. So we'll talk more about verification maybe next week or later. This is when you're trying to use logic to prove statements about programs or about hardware. Usually that they work and that they don't crash or that they don't lead to something that is unsafe. So this is a completely different structure, okay, a different set of interpretations. And in this structure, we're going to consider the substances, the white nodes, as being states of your system. This is almost a real example from a robot I was building, where we have a finite state machine and we're trying to make sure that the robot never hits anything. And it's harder than you think, because the robot only ever looks forwards. The sensors are on the front. And if it is about to hit something, you see the thing coming. You can see that you've almost hit it. Actually, the hit state isn't a physical hit; it's a laser scanner contact. It's an almost hit. So you still have time to do something about it. The robot's been going forwards. It's been happy for a while. It's now in this hit state. And the logic we put in is that if you've hit something, you are going to reverse to get away from it. And usually you do your reversing for a period of time, and then you do a turn to maybe a random direction, and then you go back to going forwards again. Now, this is roughly what your robot vacuum cleaner does when it's about to hit something. Now, the problem with this that we found, and this is quite a big robot, this is a quarter of a ton agricultural robot. The problem is when you reverse, you don't always follow exactly the same path that you took when you were going forwards. And so sometimes you end up in a slightly different place reversing. The problem is you might hit something during your reverse move. Yeah, you're trying to avoid hitting the first thing. And as part of your evasive strategy, you're now in danger of hitting another thing. And you might have a little sensor on the back that just warns you at the last minute if a hit's going to occur. And so then you need all this extra logic for what do you do if you're hitting something during your reverse escape maneuver. Yeah, so in this case, there's another turning state. We're going to turn again. We're going to go forwards for a shorter period of time, and then try and get back to where we were before. And the question is, if there's this state is called die. This means you've actually physically hit the thing, not just with your laser, but in the sense of causing £50,000 worth of damage to your robot and to someone's wall. The question is always, is it possible to reach this state or not? So can you prove a theorem that says for every other state you can be in, it is not possible to reach the death state coming from it? So under this kind of interpretation, your substances are now states, system states, and the relations are state transitions. These are saying it's possible to get from one state to another state. Okay, so in this case, it's a finite state machine that does exactly what it says on the tin. It is a machine with a finite number of states, which means we have a nice finite set of substances. So when you have a finite state machine, you can do this kind of verification through brute force. You can just consider every state one at a time and actually check, and that's called model checking. If we had an unlimited set of states the robot could be in, then we'd have to do something else, because we wouldn't be able to go around and check each of them. So in particular, remember we have proof theory, which is about proof, and we have model theory, which is about tautology. Model theory is about whether things are true and false. Proof theory is about whether things are provable. And if you're lucky, your logic will say everything that is provable is actually true, and vice versa. If that's the case with Boolean algebra and with propositional logic. So if you're lucky and that holds up, you can switch. You can do some of your work in proof theory and some of your work using model theory, depending on which is easier. So for example, showing a tautology when you have an unlimited number of substances can be very hard because you can't check everything. So if you're trying to show the truth of a formula, you might want to switch to using proof theory and derive the thing using the rules. If you're trying to show that something is impossible, inconsistent, then you might want to use the model theory instead of the proof theory, because your proof theory can just go on forever trying to find the proof that doesn't exist. But if you can show something is actually inconsistent, that no models exist, you might have an easier time. So in this kind of verification, you'll often see people switching between the proof theory and the model theory, depending what they're trying to do. Okay, the third major set of structures that are used with first order logic are mathematical structures. So pure mathematics is an application of computer science, and this involves picking a different structure. You know, we've seen there's a whole bunch of structures you can use in AI, in verification. To create pure mathematics, we're just going to pick a different structure, which normally looks like this. And what we've done here is created a bunch of substances which all have this relation called the successor relation. And we're saying this substance is the successor of the one before it, and this substance is the successor of the one before that. And conventionally, we put labels on these substances, and we just give this symbol that we call 1, this symbol that we call 2, this symbol that we call 3. They're the same symbols that we use to name the church numerals, but at this level, they're just symbols. They're just things that can be typed on a keyboard. So what you have here is obviously it is a countably unlimited set, precisely because the labels have a one-to-one correspondence with the natural numbers, and you have this successorship relation. So you know this structure then gives meaning to statements like this. If we say for all x there exists y and there exists z, such that x is the successor of y and y is the successor of z. Is that a tautology? Anyone? What does this mean under this structure or this interpretation? So that means for any number x, you can always find two other numbers so that x is the successor of something, and that something was the successor of something before it. Okay. So is that true for the natural numbers? It's saying for any number you can find a number 1 less than it, and you can find a number 2 less than it.
Yes.
For the natural numbers?
Natural numbers. Yeah, I think so, yeah.
So the natural numbers start at 1.
Oh,
So
never mind. Sorry. No, that is false. Isn't that
it's false. Yeah.
Isn't that the positive integers?
Yeah.
I thought the natural numbers was just. Never mind.
Natural. Actually, people argue about whether 0 should be considered a natural number or not. But usually they're 1, 2, 3, and so on. Yeah. Okay. So if we used a different interpretation, if we used this interpretation corresponding to the integers, then it would be true. Yeah. If you use the interpretation that these quantifiers are ranging over integers, now the formula is true, but the formula is false under the natural number interpretation. So for arithmetic, you actually have a choice of a few interpretations. You can choose the natural numbers, the integers, and so on. But normally when logicians talk about arithmetic, they mean, yeah, usually it's the integers they're going to use, because you want to do subtraction as well. But it normally doesn't include fractions or real numbers or imaginary numbers or anything like that. So you notice these mathematical interpretations are actually very simple. There's just a handful of these corresponding to those different number system. And they're just particular choices of structures, which are much simpler than the structures we use in other parts of computer science if we're doing verification or if we're doing AI. Because in AI, there's millions of ways you could set this up. There's millions of substances and relations, and A could be B's father or B could be A's father, and all these things are going to move around. But in mathematics, you have this really simple structure. There's just a bunch of substances, and everything's the successor of something else, and that's all there is. So mathematics is actually quite a simple application of computer science compared to some of those other domains. Okay, so that's the model theory. Okay, those things are all called first order structures, and they correspond to the first order logic in the grammar and the proof theory. Shall we keep going? Do you want to stop, or do you want to keep going?
Yep, keep going.
I don't mind keep going.
Yeah, no, I've been looking forward to the meta logic.
Okay, yeah, this is the fun bit. If this doesn't make sense, okay, this may go on for a while again. If it doesn't make sense, or if you're dying of tiredness, remember we are recording this, so you can always go and make a cup of tea and come back and watch the recording later on. And I'm teaching it with that very much in mind. You know, you teach differently if things are recorded from if they're not being recorded for that reason. Okay, let's do this then. Let's do the meta logic. I've always wanted to do this. Okay, some basic metalogic properties of first order logic before we get to the fun ones are soundness and completeness. And it's easy to get confused with these names. Okay, these are the same properties that we saw for propositional logic. And as for propositional logic, first order logic is sound and it is complete in the sense that we have previously seen. So remember, these two properties mean anything that is provable is also true in the sense of your model theory. And anything that is true is provable. Okay, so we can write that using the notation we saw last week. So you have phi proves psi if and only if phi models psi. So if phi makes something true in the model theory, then there is definitely going to be a proof taking you from phi to psi in the proof theory. And vice versa, if you can find a proof going from psi to phi in the proof theory, then your model theory can show that assuming phi makes psi true. Is this a surprise to anyone?
No, but I think, haven't you pulled a bit of a blinder up the top there? You said Gödel's syntactic completeness theorem instead of...
Yeah, okay. Now there is some horrible misnaming of things which we are stuck with, okay? So Gödel is famous for what is called Gödel's theorem. And the full name of Gödel's theorem is Gödel's first semantic incompleteness theorem. Before he did that, you know, his lesser work, you know, his first album was the completeness theorem, which is a easier theorem, simpler theorem. And here we are talking about completeness in this sense. This is the same sense that we discussed it in propositional logic. So soundness and completeness, you normally talk about them together, means that if something's provable, it's true, and vice versa, if it's true, it's provable. So if you've heard of Gödel's incompleteness theorem, which is the big album, you can get very confused because you've heard this famous result that first order logic is semantically incomplete. The type of completeness we're talking about here is a completely and utterly different thing in the completeness theorem from the incompleteness theorem. So we call this syntactic completeness. So these properties together, syntactic completeness and soundness, give you this one-to-one relationship between provability and truth. Anything that is provable is true in the model theory, and anything that is true in the model theory is also provable. Right, I've stated this without proof if you're interested to see the proof, it's in Boulos' book I've given you. Not an especially easy read. Not going to examine you on that stuff, but it's there should you wish to convince yourself that it exists. That is the completeness theorem. Now this is lovely because it justifies the ability I mentioned in verification, that sometimes you want to use some proof theory and sometimes you want to use some model theory. And this, as with propositional logic, it tells you that you're allowed to switch between them anytime you like. You can show some things are true and other things are provable. And whenever something's true, it's also provable. And whenever it's provable, it's also true. So you can flip between and use whichever method is the easiest one to use. So this was a nice result. You know, this was Gödel in his modernist phase, if you like. This was when everything was going along according to Hilbert's program. You know, this is what was supposed to happen. This is showing that the logic is behaving in the way you want it to behave. The proof theory is actually giving you results that are true, which is usually what you want a logic to do for you. Gödel's incompleteness theorem. Full name, Gödel's first semantic incompleteness theorem. This is not the opposite of the completeness theorem because the word complete is used in a different sense here. This is used in the sense of semantic completeness. So first order logic is both syntactically complete and sound and also semantically incomplete. And semantic incompleteness is the famous result. It says any logic that is powerful enough to represent arithmetic, i.e. the natural numbers addition and multiplication, any logic that is able to do that must be either semantically incomplete or semantically inconsistent. And incomplete means there's a formula, G, let's call it, after Gödel. There is some formula which either can't be proved or its negation can't be proved. Okay, so this is a statement which the system is unable to make a decision about. We're going to create this thing, give it to your proof system. You know, is it true, or rather, is it provable? Is its negation unprovable? And the system is unable to deduce either of these conclusions. You know, you're going to break your system by asking it a question that it can't answer. Now, again, this is where the sci-fi movies come from, where the robot is saying does not compute, does not compute. It's a statement that the system can't handle. So you either end up with no proof of G nor not G, or you end up with the proof of both of them. You end up with the statement both being provable and its negation being provable. Notice I'm at pains to not use the words true or false here because Gödel's theorem is about proof. It's about the proof theory, not about the model theory. And true and false only show up in model theory. Here we're talking about whether things are provable or not provable. So what is this weird formula going to be? Something you can either end up being unable to prove it or its negation, or you're going to have to prove both. So you know, consider a formula like there is a car in the car park. Yeah, you know, if that was the Gödel statement, we'd be in a case where your system can neither prove that there's a car in the car park, and it also cannot prove that there is not a car in the car park. It just can't say anything about it. Or if you choose to go the other way, you can have a version of the system that can prove both. It will go and prove that there is a car in the car park, and it will prove that there is not a car in the car park, which would be very bad. Now, usually you can prove unambiguously whether there is a car in the car park or not. That's not the kind of formula that G is going to be. G is going to turn out to be a self-referential statement, and we've mentioned these before. Roughly in English, you can translate it as system S cannot prove statement G, where system S is your logic and G is itself. So roughly the sentence is saying your logic can't prove this sentence. And, you know, take a moment to think about this English version as a human being, you know. Consider the sentence, Charles Fox cannot prove this sentence. Okay? So is that sentence something that you can prove? Because you're not me. Can anyone explain why that sentence is provable or not? And you have to do it without using the words true or false.
It's interesting. You put a spin on it because we went over this the other day, but I hadn't thought about a different logic. I think, well, different logics will interpret it differently. So another logic could be incomplete or inconsistent on the same sentence. It doesn't say anything about that logic.
Mm-hmm.
So another logic can prove it. Another logic could, or the same logic could be incomplete or inconsistent on that, right?
Yeah, that's right. So this is informal. We're dealing with English and people here. You know, roughly, I've got a system in my head that can do certain things, and you've got a different system in your head. Okay, and the sentence says Charles Fox cannot prove this sentence. So can you prove the sentence? Can you give me an argument for
Sure, I can.
for that sentence?
Yeah, my logic can prove this sentence.
Why?
Why can my logic prove this sentence?
Yeah. So to do that, you're in fact going to have to
My logic
explain why
can say
I
things
can't.
about my logic can say things about your logic is why.
Mhm.
That's the foundation of meta logic is when we can't use the system to talk about itself, it's using a different system to talk about it.
Mhm.
And then it
So
turtles all the way down from the.
For you to prove that sentence, you are going to have to give an argument precisely about why I can't. Yeah. So how can you do that? Can you explain why I can't prove it?
Like in this English version, I would
Yeah.
have to know things about your logic that I don't necessarily know personally. So if I understand what's being talked about here, because my logic would have to intimately understand the composition of your logic in order to say exactly, specifically, what it is about your logic that makes that logic unprovable. But actually, in general,
So what would happen if I could prove this sentence?
well, yeah, well, obviously, if you could prove this sentence, then the sentence is true. The sentence falsifies itself. And if you can't prove it, then, none. But, so I can say that in my logic about your logic. But whether or not your logic can say that about itself is.
Okay. So look, from your point of view, then you're going to give me a proof by contradiction, probably. You know, assume for a moment that I could prove that sentence. Okay. So remember how we do proofs by contradiction. You assume something and then you show that it leads to a contradiction. And then
Yeah,
the thing you
such as the
assume
fact
is
that,
correct.
so that's something I'm getting caught up on. I'm not exactly sure what it is. I think it's on the difference between what isn't a logic. It's because we're using like English semantics.
Mhm.
So yeah, we can go through like that regular order of things. But
So okay.
surely your logic can also go through that order and say that your logic can't prove the sentence. So can't your logic also make that same statement?
Well, that's exactly what we just assumed. Yeah, assume that I can prove it. Yeah. So yeah, let's assume that I can prove it. So what's going to happen now?
Well, your logic can prove the sentence that it's been stated within its own logic, and that means that the statement that you've made within your logic has been self-falsified.
Yeah, we've derived the contradiction, right? Because the statement says that I can't prove it. And when you derive a contradiction, you are going to say, therefore, the assumption is impossible. Okay? And then, therefore, you can conclude the opposite of the assumption.
Okay, I guess my question is, why did we bring in a separate logic in order to talk about that?
Precisely because my logic isn't good enough to prove it.
Yeah, but
so my logic can't prove the sentence. Precisely because that's what it says on the tin. So we had to bring in your logic to come and do it instead.
But my logic hasn't proved that sentence either. It proves that you can't prove it.
But that's exactly what it says. That's all you have to
Oh
say.
my god. Oh, I need to go to bed for like another 10 years. Wow. Incredible. Okay, we're on, yeah, never mind. Oh my god.
So look, in Zen Buddhism, they give you sentences like this and ask you to sit down and think about them for 5 hours at a time. So, I'd recommend that as an exercise for everyone. Yeah, try putting your own name in place of my name and go and have a little meditate on whether or not the sentence is actually provable.
I found a fun paradox recently. In the X-Files I was watching, and it said deny everything. And so if you accept that, you're not denying everything.
Mm-hmm.
But if you're denying everything, then you aren't accepting that you're denying everything.
Yeah.
So that was quite a good one.
So they mean deny everything apart from this.
Yes, which isn't quite so catchy, but
Good.
I quite enjoyed it.
Good. So look, just a reminder, it's taken me about 20 years to understand this. I'm just going to give it you on a slide now. That's how easy your lives have got. This is not evident in GEB either. I think there are some either errors or misunderstandings in a couple of places in GEB. I think Doug was not so hot on the model theory as he was on the proof theory. Look, syntactic completeness is a different thing from semantic completeness. So Gödel's completeness theorem says that anything true is provable and vice versa. So in particular, you are now allowed to invoke the completeness theorem to go and talk about truth. So on this slide, I was very careful not to use the words true or false, yeah? And I didn't let you guys use true or false either. We were only talking about provability. But you can talk about true and false by invoking the completeness theorem. So when we talk about that sentence, CF can't prove this sentence, you may invoke the completeness theorem such that if this thing is provable, then it actually is also true. And if it is true, it is also provable. And you can make that jump. Now, incompleteness semantic incompleteness is a different property. This is the semantic incompleteness property, and it involves symbols with negation in them. There's nothing in the completeness theorem about that symbol, but in the incompleteness theorem, it's all about that not symbol. So first order logic is syntactically complete, and it is also semantically incomplete, and it is extremely confusing using the word complete in those two sentences. I really wish they'd been given different names, but that's just the way things are. And there's at least one passage in GEB I found where they seem to get confused. Also, Gödel's first semantic incompleteness theorem is distinct from what is known as Church's theorem, or Church's undecidability theorem. So you remember Church's result we saw in the lambda calculus lecture, right? Church showed that there are uncomputable functions. There's no algorithm that can fully evaluate them. Now it's possible to translate Church's findings from lambda calculus into first order logic, and if you do that, you will get the equivalent result, but it's called Church's undecidability theorem. So this theorem is saying there are some formulas which have no algorithm which can prove or disprove them. So again, this is not quite the same thing as the Gödel semantic incompleteness theorem, because this theorem has these two cases, and it says for any logic that can represent arithmetic. So this condition doesn't apply to Church's theorem. Gödel's theorem only applies to logics that can represent arithmetic. And if you can represent arithmetic, then it says you can either have incompleteness or you can have inconsistency. If you have inconsistency, then the system certainly can prove G, and it can prove not G as well as a bonus. And if that's a different kind of claim from Church's theorem, just saying that there are formulas out there that no algorithm can prove anything about that. Gödel's theorem gets all the fame, but there are these other theorems around as well. Okay, if everyone is still alive, let's try and have a look at the actual proof. We'll give an overview of the proof. And my overview is based on another overview given by Nagel and Newman. I've not given you Gödel's original paper because it's really, really hard. But I've given you Nagel and Newman, chapter 7. This is a very famous and classic representation, not a representation, a representation of Gödel's work, which is more rigorous than what you find in Gödel-Escherbach, but not quite as rigorous as Gödel's original proof. So it's just about understandable by the likes of us. So my version is a simplified version of their simplified version of the original paper. I did make it through the original paper once. It was hard work, so I'm not going to inflict it on you at all. But I am going to inflict Nagel and Newman. We can do things a little easier nowadays than in Nagel and Newman and Gödel's paper, because nowadays we have computers and we're very used to the idea of ASCII encoding. So Gödel's original paper had this breakthrough idea that you can take a formula and convert it into a number, which at the time was revolutionary. But hopefully for anyone who's done computer architecture with me before, it's a completely trivial observation nowadays, in part because of what Gödel gave to us. Nowadays we are very used to looking at a string such as this one and converting it into a number. So in the hexadecimal system, we consider strings which have 16 symbols in them, labeled from 0 to F. and we make strings out of those symbols, and we apply a base system. We interpret this string using the system of base 16. And as we all learned in our computer architecture class, that means you're going to take each symbol, or more formally, we're going to take the numerical value of each symbol. So F is a symbol. Putting it in quotes means convert it into a number. So when you see F in quotes, this is just like in a programming language where it's a char. You know, here it is going to get converted to the number 15. That act of putting it in quotes says convert it into a number. So we're going to do 15 times 16 to the 3 to get that bit. We're going to do 2 times 16 to the 2 to get that bit. We're going to do, what is C? 10, 11, 12, yeah? 12 times 16 to the 1 to get that bit. And then 3 times 16 to the 0. And then we add them all together, and we end up with this number. That's to show that it's written in base 10. The subscript just tells us what base it's in, which is actually completely ambiguous when you really think about it, because that number itself could have been written in any base. That's also a 2 in base 2, but I think we assume that this is always written in base 10. So look, we're very happy with the idea that we can take a string of symbols, and by putting it in quotes, we're going to interpret it as a number, yeah, as a natural number. So does this still make sense to everyone? Do you remember this from first year?
I hope so.
Yeah. So you can see the purpose of the base system is that it gives meaning to strings. The characters themselves already have a meaning. You know that F is meaning the number 15, 2 means the number 2, C means the number 12, 3 means the number 3. That's meanings of the characters, but the meaning of the string is given using the hexadecimal base system. The string means you're going to take each of those values and multiply them by a power of the base and add them together. And that's how we give a meaning to a string. So if you write this in a hex editor, you can see there's this interplay between this being a sequence of characters and it being a sequence of digits from 0 to 15. And also you can read this as a number. You can just look at that string and it means this number. So when we put something in quotes here, it's going to mean the numeric value of. And I've chosen this notation because it's exactly what we have in many programming languages. If you take the value of A in a language like C, you will hopefully get the ASCII code. You can just interpret that as an int, the number 65, and B is the number 66, so on. So let's assume we are going to work in ASCII now. So hex is base 16, ASCII is just base 256, right? ASCII gives you a set of 256 symbols, and let's view ASCII as another base system. So if I take a word like hello, I can view that as a number. You know, it's going to be the value of H times 256 to the 7 or something, plus the value of E times 256 to the 6, and so on. Now, what we really want to do is encode logical formulas. And remember, logical formulas have a few weird symbols, right? We've got our favorite upside down A's and backwards E's and Boolean stuff and arrows. So let's assume that we modify ASCII a little bit. There's a lot of spare characters in ASCII that do all these weird things like ringing a bell and deleting characters and stuff. Let's assume there's a bunch of those slots that we can use to represent all the characters that we need. Okay, so we've got 256 symbols. most of them are the same as in ASCII, representing letters and numbers and all the symbols on your typewriter. And we've also got the ability to represent these logical symbols as well. In the 1970s, they used to make keyboards with all these logical symbols on them. They had extra keys, so you could press combinations of keys because it was so common to do AI in this way. So, yeah, it's an ASCII-like encoding. It's got 256 symbols, and we are using the base system to interpret strings as numbers. So in particular, we can take a logical formula, like this one, rewrite it in terms of the base system and get an integer as its numeric value. So here, that symbol upside down A is, here I've given it code number 1. Remember, ASCII starts from A is 65. There's a bunch of space at the beginning of ASCII encoding. So that first symbol then, that's going to give us 1. Remember, A in quotation marks is 1. 1 times 256 to the power of 10. And it's to the power of 10 because there's 10 symbols in the formula. Or 11, because we've got 0 at the end. Okay, so the next symbol is X. So here we look at X, and X is going to have a value in the ASCII code, somewhere between 0 and 255. And we're going to multiply that by 256 to the power of 9, and that gives us the next bit. And it's exactly the same as we did for hex. Okay, we're going to go all the way through this formula. But the last symbol is a closing bracket. That has an ASCII coding as well. That gets multiplied by 256 to the 0. And so when we look at a string like this, that string, you don't even have to convert it, right? It's just directly representing this number in just the same way that this hex code represents this integer. This string represents this integer. And if you can get your brain to think in base 256, you never need to convert that integer into base 10 at all. You can just look at this thing and you just know that that's an integer. It's a string in quotes. It just means a big integer. It's like looking at this number tells you how many 100,000s there are, whatever. This number tells you how many 256 to the power of 5s there are. So the trick is to view this string as a single very large number. And you can do this for any string. You can take your favorite novel and open it up in a text editor, and you look at it and you see a massive string. If you view that string just as a number in base 256, now you're just looking at a single great big integer. You don't even have to convert it. You're just viewing a big number. And this gets into these crazy legal questions that some numbers are illegal to know. You can represent many things as a large text file. You can represent government secrets or cryptographic keys or libelous information. And just the act of knowing that number that is expressed in base 256 may be illegal in some cases. Banned integers. They're very large integers. Though you can see this one only has, I think, 11 characters, and it's already getting pretty big. So a whole novel full of ASCII text is going to be a very large integer. Okay, so Godel used a more complicated system based on prime numbers, but it's the same idea. The nice thing about ASCII is that you can just see the meaning of each term directly, because this thing is a number. This thing is a number in base 256, but you can also look at it. If you look at what's inside the quotation marks, you can see what it actually means, because it's a logical formula. You can see this both as an integer and as a meaningful piece of logic in the same set of pixels on the screen when you look at it as a human, which is, it's not possible to do that in Gödel's original system. Gary?
Yeah, just add in, I remember reading about the value of pi, because it's a rational and non-repeating, that pi itself could contain all the legal documents that sort of ever exist and so on and so forth. And
Yeah,
was,
it does. I think it has to do. Yeah.
Yeah.
So yeah, if you wanna send child pornography over the internet, say you just find where in pi those digits are, and then send over the numeric location of where to start and where to stop. The problem
actually
is
there's a proof of concept file system called PyFS, which stores everything on your disk as an offset and a width in pi.
That's amazing. I'm guessing it's going to remain at the proof of concept stage for some time.
It has interesting algorithmic complexity.
I mean, if you really want to sneak a government secret in an aeroplane, all you've got to do is put a ruler on your person, on your t-shirt, and just mark the location. You have here's 0, and here's 10, and you've just got to draw a big arrow on your t-shirt showing a point on the line, and that number could contain all the decimal places that you ever need if you can do it accurately enough. And if anyone asks, it's just a triangle drawn on the t-shirt.
One thing that's interesting, again, you point out there, because then you're heading into steganography almost, is that in a lot of things like this, you don't just have the number, you also have a function or a methodology for either converting to that number or extracting the information from that number, which would be, in Gödel Let's Go Back, they talk about, well, representation. It's all about representation. And obviously, if I have a method for encoding the number, then I can encode that method as a number. So in theory, there are numbers which are not just illegal, but knowing the number makes other numbers illegal.
Yeah, right, because your method is a program, and the program itself is just a big string, and the big string is just a number. So yeah, programs are numbers as well. You open a program in a ASCII text editor and look at it in this way, and it's just a big number written in base 256. So yeah, I think it's a beautiful thing to look at something like this and be able to see it in both ways. You can see this instantly nowadays as representing that number. It's just a string in base 256, just like a string in hex representing a big number. And you can just look at it and you can see that big number, and at the same time you can see the intended meaning of it because it's written for you in plain logical syntax. It means for all x there exists y such that x and x equals y. But it's also a big number at the same time. Okay. That gives us a way to read a formula as a number. We can do the same thing for proofs, because remember, proofs are programs. A proof is just a set of instructions for when to apply a bunch of rules in a certain order. Especially when you look at them in the Fitch notation that we saw today. So, a proof is a program, and we saw this in Gary's proof of the MIU system. It's a program that says apply rule bang in position 12 and then apply rule pop at location 9. So you can write down a program describing your proof. Again, in our extended ASCII alphabet. So that means you can take your proof and convert that into a number as well. Or again, you don't even have to convert it, you just look at it. Let's say you have a proof like this, okay? This is a proof in the MU system. And the proof says first apply rule bang at position 12 and then apply rule pop at position 9. So we can read that proof exactly as we did for formula. We're just going to read it as a number in base 256. Each of these things is an extended ASCII character. You know, the B has a value. It's that number times 256 to the 13, blah, 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 all the way up to the value of that ASCII 9, which doesn't have the integer value 9 because it's an ASCII character, times 256 to the 0. So in fact, if you take this proof and convert it into decimal, it's this number. And you can view this number as an attempt at making a proof. You know, let's say we're trying to prove MU in the MU system. You can consider all the possible proofs that you might ever come up with. You know, all these big ASCII files that you're going to write as programs. And this particular one is the 1995 blah 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 2/160th possible proof that you could have written down. So we've converted formulas into numbers, and we've also converted proofs into numbers. In fact, we haven't even converted them now. We're just looking at them with our eyes as big numbers written in base 256 in extended ASCII. Okay, so once we're happy that both formulas and proofs are just numbers in a suitable representation, we can then consider, let's go straight to this first. We can then consider making a numeric function which checks if a proof works or not. Now, is it always possible to check if a proof works? If I give you my attempt at a proof and I ask you, is the proof correct? Can I always do that? It's exactly what I'm going to give you guys for homework when I give you these first order logic proofs to look at. Yeah, you're going to work through the proof and say, is each line correct? Does it actually apply the rule that we said was being applied? Okay, so this is possible. This is a completely mechanical process. If I give you a proof, anyone can check the proof. You can do it with a machine. You can do it with a human. Because all you're doing is checking. You're just saying, does each line actually follow from the line before it? And is the thing that comes out of the end the thing that we said we were going to get? So consider writing that as a program or as a function. Yeah, here's a Python style notation. Let's say that the lowercase p is the integer number, which is equal to the numeric value of proof curly p. So here curly p is the actual proof. That's a logical conceptual entity, and little p is an integer, a natural number in this case. P is of type natural number. And similarly, little f is going to be the natural number corresponding to formula curly f. And again, that's what the quotation marks mean. They mean the numerical value of. So yeah, here's how you write a simple proof checker. And I think did someone actually do this for the MU system? Did someone actually write one of these? And it goes through and it checks if each step of your proof actually works. You know, it applies the rules in the order they're given in the proof. So, you know, to do this then, first of all, you take your integer p and you decode it from being an integer into an actual proof. Yeah, so this is roughly parsing, if you like. You're going to do the same thing for the formula. You're going to convert it from being an integer into an actual formula. And when you've done that, you're going to have a big for loop, and you say for each line of the proof, find what rule is being applied, check if all its premises are satisfied from the theorem that you currently have. Yeah. Check the inputs to the rule are good. Then you apply the rule, probably by calling another little function, apply my rule, and that will give you as an output the new theorem. And then you go around again. Now you find the next rule. You apply one rule at a time from the proof. And again, someone mentioned this looks a lot like assembly coding. You're giving a set of instructions for what to do at each step and applying them as you go. And then at the end, you say, does the final theorem equal F, the thing that you were looking for in the first place? So this function is proof. It's just a simple function which takes two natural numbers as input and returns a Boolean. It's just a normal arithmetical function. And it's something which we can always construct because we're just checking the proof. Okay, now let's consider proofs about proofs or metaproofs. Let's consider a simple example of this. We now have a numerical function called isProof. Okay, so if I give you a claim like, I don't know, the square of 2 equals 4. Yeah, this is an arithmetical claim, and you can go off and check it. And in this case, it works because the square of 2 is 4. isProof is just another arithmetic function, just like squaring is an arithmetic function. So we can now include isProof in the set of functions we can ask questions about. So here we've made a statement which says, for all natural numbers p, it is not the case that p is a proof of 1 plus 1 equals 2. Now, is this true or false? This is a formula. Is it?
Yeah, if we're iterating all proofs, I don't know how we're iterating. Maybe we're just incrementing. If we're expressing them all as a number, maybe we're just incrementing through all of the proofs. There are a lot of them that are proofs, but are not proofs of the formula specifically.
Mm-hmm. So what does the formula say in English?
It says 1 plus 1 equals 2, but our formula,
the whole formula, all of this.
Yeah, is saying that for all proofs, as in p as some number.
Mm-hmm. Yeah, candidate
that
proofs.
we can iterate over. Yeah.
For all possible proofs, p.
Yeah, it's not the case that the proof is a proof that 1 plus 1 is 2.
Yeah, good. So look, notice that this thing is in quotation marks. And that means we're reading it as a number written in base 256. Yeah, so this thing is just a string or an integer. Strings are just integers in base 256. We're not doing Unicode, right? ASCII. Yeah, so this thing says, it says there is no proof that 1 plus 1 equals 2. Now, is that true? Is there a proof that 1 plus 1?
I think I just misunderstood that. So that's the difference between for all p versus there is a p.
Mm-hmm. So yeah, this says every possible candidate proof is not a proof of 1 plus 1 equals 2.
Yeah, that's not true though. Yeah,
so this thing is false.
Mm-hmm.
And it is false because we know, or we hope there is a proof that 1 plus 1 equals 2 if we've set up our logic in any sensible way. Yeah, there should be a proof somewhere that 1 plus 1 equals 2. and this formula is claiming that no such proof exists. So this formula is false under any sensible logic and sensible model theory. And we can prove that this is false by showing what the proof of 1 + 1 = 2 is. If we can create that ourselves and write it down and show it to someone, then we can convince them that that proof exists and therefore that the formula is false. So in contrast, this formula is true. Okay, why is this true?
Because we hope that there is no proof that shows that 1 + 1 equals something that 1 + 1 does not equal.
Yeah. So again, if we've set this up in any sensible logic and model theory, then there isn't a proof that 1 + 1 = 3. Good. So it's harder to prove this. Okay, this is easy to prove because all you have to do is find the proof that 1 + 1 = 2 and show it to me, and that will convince me that the big formula is false. It's harder to prove this because now you're showing the lack of a proof rather than the existence of one. To show the existence, you've only got to find one proof, but to show this, you've got to convince me that every possible proof is never going to produce 1 + 1 = 3. Now, this is the difference between showing MII is provable and showing that MU is not provable. Question from Gary?
Yeah, just wondering if you could show that there is a proof of 1 + 1 = 2. It would obviously contradict the 1 + 1 = 3 if that was a valid route to demonstrating this.
Yeah. So you'd need to do some arguing, yeah? Well, you need to apply some extra rules of logic to do that. So yeah, okay, I'm willing to accept that 1 + 1 = 2. So why does that prove that there's no proof that 1 + 1 = 3 as well?
Because we're using the same initial term, it would be we couldn't equate them as such. We couldn't then say 1 + 1 = 1 is equivalent to 1 + 1, because that would say then that 2 is equivalent to 3.
Yeah. And why is that bad? Why shouldn't 2 be equal to 3?
Because it's in this world, it's not the same thing.
Yeah, so you're going to try and derive a contradiction, probably, aren't you? You're going to say, suppose 1 + 1 = 2 and 1 + 1 = 3. Suppose for a minute they were both true. Yeah, so now you can show that 2 = 3. So, I don't know, subtract 2 from both sides. Now you can show that 0 = 1. And that's usually held as the basic form of a contradiction. From 0 = 1, you can prove pretty much anything. But formally, you'd have to go through the rules of logic and actually demonstrate that you've obtained a contradiction, and then you can invoke the rule of proof by contradiction to get back to your proof. Yeah, so that's probably how you prove this. Yeah, by contradiction. Good. So some of these formulas are much harder work. Okay, this is a tiny little theorem that was proved by a guy from my Cambridge College called Andrew Wiles, called Fermat's last theorem, and it took, I think, over a decade and many thousands of pages of proofs to show this. This says for all natural numbers greater than 2, there exists a, b, and c such that a to the n plus b to the n equals c to the n. So for 2, there are, it's like the Pythagorean theorem, but it says you can't find integer versions of the Pythagorean theorem for values higher than 2. So if finding the truth value of a statement like this is very difficult. Yeah, this is saying does there exist a proof of this or not? So we just about know that there actually is a proof. The thing is, it's 2,000 pages of human created mathematics, and there might be bugs in it. Yeah? If only we had some kind of computerized theory of logic and computation that could actually check a mathematical proof like that, and make sure that every step was actually following the rules of logic.
I'm sure I remember. I'm sure, I don't know if this is the author Simon Singh. I seem to remember a book that I read about Fermat's last proof by Simon Singh, and Andrew Wiles had done the theorem and he'd done something, and then there was a very small error in it, and then went to his basement for another period of years and resolved it in some way or something like that. And I seem to also recall that there was the statement had come from, it was something that was put in a margin, and it said, "Oh, I've proven this, but I'm not. It's too simple, so I'm not going to write it down." And it was, and then left it there for years. And
yeah, that was Fermat's original proof. Yeah, it was a margin note saying I've found a nice little proof of this. Andrew Wiles is going to be really annoyed if that little proof ever shows up and actually works.
Just a little fun fact on Star Trek Next Generation, they actually refer to Fermat's last theorem as not being proved, but obviously this was before Andrew Wiles proved it, so that was quite funny. Obviously that's the year 2400 or whatever it is. So.
Yeah, there is progress in mathematics still. Goes quite slowly in areas like that. Okay, cool. So yeah, that's just to give you an idea for giving proofs about proofs. Yeah, that proving this formula is a different business from proving this formula inside the quotes. Here we've taken 1 + 1 = 2. We've considered it as an ASCII string, which is an integer, and now we're proving a theorem about that integer. And similarly here. Now, again, this is a different business from just proving whether or not 1 + 1 = 3. Here we're proving whether or not a proof exists about 1 + 1 = 3. So we're going to use this kind of idea to break first order logic. Okay, this is how Gödel blows up Western logic and creates postmodernism and all the rest of it. We are going to construct a formula which is undecidable and which will lead us into one of those two states. Either you can't prove it for its negation, or you're going to have to be able to prove both of them. And by Gödel's completeness theorem, we are allowed to talk about truth and false because everything that happens in proof theory gets mirrored in the model theory under the completeness theorem. So that means that this formula, it either has no truth value, either it is neither true nor false, or it has both. It's both true or false, but it can't just be one or the other. It's either neither or both. Okay, so here's the battle plan. Okay. Remember this notation for substitution, right? X = A with B for C. This means you're going to take formula A, and wherever you find a C, you're going to replace it with a B. That's the same notation we have in LAClecture. Now that's just a little operation on strings, very easy to do, can be written as a program, and therefore it can be considered in Gödel number space as a function of integers. Let little x be the integer version of formula big X, and so on for the other numbers. So A is a formula, little a is its integer value in ASCII in this case. No, we are writing this the other way around to be consistent with Nagel and Newman's book. This says sub CBA. This says A with B for C. So sub ACB means A with B substituting for C. Okay, so if you're reading Nagel and Newman's book, the C and the B appear this way around. So we're going to use their notations to be compatible with their book. Okay, so just think about what this means for a moment. Okay, this is just a numerical function. It takes 3 integers as an input and it gives an integer as an output. And it's very easy to define and compute because it's just doing that on the ASCII strings. Yeah, one line of Python, regex. Okay, keep that in your pocket. And now let's consider this crazy formula. When you see consider, that means we're going to pull a totally arbitrary random thing out of nowhere and just think about it. And we're not going to tell you yet what it's for or why we're looking at it. Okay? Yeah, we're allowed to do that. We're allowed to consider things. So let's consider this formula, which we will call H. I remember we talked about free and bound variables. Formula H has a free variable y. So y is not yet defined. It's just a symbol that can get bound later on. So H says for all p, for all possible proofs, p is not a proof of this thing. Now this is the thing that we're pulling out of thin air, okay? And it's based on the substitution we just defined. What can we say about this? This notation means you take the string for a formula y. So this lowercase y is the string ASCII value of formula big Y. Y is a real formula, little y is just a number. And wherever you see the character y in that string, you do a search and replace, and you fill it in with a copy of the original formula. Right? You're going to take your formula as a text file. You're going to do Control A, Control C. You've made a copy of the whole formula. Okay? Now you do search and replace, and you say wherever there is a y, Control V. So if your formula's got any y's in it, it's going to end up being a lot longer than it started, because everywhere there's a y now gets a copy of the whole original formula. In particular, that means there's going to be a bunch of new little y's that have got pasted in there. So yeah, open your formula, Control A, Control C, search and replace, lowercase y with Control V. Go. That's all it does. Nicely definable little function. Now you can see there's this recursion. Yeah, we've got y entering this in 2 places as y, and also the integer value entry. And this is your trigger warning that something is going to happen, like Turing did, like Church did. This is always how you blow things up. You get them to make computations about themselves. So at the moment, H doesn't have a truth value because it has a free variable. Okay, H is contingent because it depends what y actually is, or what we choose to use for y. In the next step, we are going to replace that y with something else. So we're going to bind it, we're going to perform this substitution, okay? And this is going to create the Gödel formula, or the Gödel sentence. So we're happy with H. All we're going to do is create a new formula by looking for all the little y's and replacing them with a copy of H, which sounds suspiciously similar to what this numerical function sub was doing. But at this point, we're doing it in the logic itself. So if we do that, all I've done here is I've taken h. This was the thing we plucked out of thin air, right? I've just taken that formula, and wherever I see a y, this is not a y, this is an integer. This might be the number 13 at this point, because we've turned it into an int. So that one isn't going to get affected. Wherever we see an actual y, we're going to replace that with a copy of h. So this one is going to get replaced by a copy of h, and this one's going to get replaced by a copy of h. So when we do this, we are going to end up with a cent G coupled with a Gödel number little g. Remember, the little letter always means the integer value of the logical big letter. So at this point, remember we made this change to big G. We've substituted h for y. That means that the Gödel number ends up undergoing this transformation. This is the equivalent transformation in integers to this transformation in logic. Okay, so the Gödel number is now going to change, and it's going to change according to that substitution operation. You're going to take the formula for h. Again, you're going to look for all the instances of the character y in it, and you're going to replace them with h's. And then you're going to take the Gödel number of all of that. So this means we've got two ways of viewing G now. This way of viewing little g is a purely arithmetic operation. We're taking the integer h, the integer for y, and performing that substitution on it. If we view it the other way around, we can take the logical sentence big G, and we know that little g is the Gödel number of big G. So here I've inserted quotation marks around the definition of big G. And we know that these two things have to be equal. Okay. Now, what do you notice about these two equations? Well, take a look at this term and take a look at this term. Okay. These terms are the same. So this term here is little g. It's the Gödel number of the Gödel formula. And we know that little g is the Gödel number of the Gödel formula, which we can write like this. Okay. So here, I've made an equality like this. There's that term again. There it is there. We can substitute everything back into the definition of G, and we end up with this. And remember, it's because of this term. This term appears inside the quotes here, and it appears outside the quotes here. So substitute all of that back in, and we now see that G is now saying this. It is saying for all possible proofs P is not a proof of G. Okay? And look, here G is in quotes. Here G is not in quotes. Here it is in quotes. And being in quotes means we're considering it just as an integer. Remember, P, lowercase p, is an integer, because it's the Gödel number for a proof. Big G in quotes is the same thing as little g by definition, which is also an integer. And is proof is a nicely defined function taking two integers. So what we've done here is we've created the formal logical version of the English sentence we saw before. Right? Formula G says Formula G does not have a proof in your logic. Right? G is representing a statement about itself. So the question is, what are we going to do with this, right? Is this thing provable or isn't it? And is it true or is it false? Okay. Sentence G says, for all possible proofs, there is not, P is not a proof of sentence G. So what would happen if G was provable and therefore true?
If we could prove G, then, well, within our logic, we've just disproved G.
Mm-hmm. Yeah, so if G is true, then it must be false, because that's what it says. Well, equivalently, if it's provable, then it isn't provable. Okay. So what if G is false? What would happen the other way around?
Well, if G is false, if it's not true, then it's also saying that since there is full proofs in our logic, there is no proof. So if it's false, I mean, it's exactly the same as the other one, but I need like 2 hours and some pen and paper and to answer your question properly. And then I need to redo that like 5 times to be able to say it with confidence.
Keep trying for about 20 years, I recommend. So yeah, G says that G is not provable, and by the completeness theorem, there's a duality between provability and truth. So you can interpret this as saying G is false. Yeah? G says this sentence is false. So when you go to the model theory, the model theoretic version of this is called Tarski's theorem, which is the less well-known analog of Gödel's theorem, but for model theory. So remember, Gödel is working in proof space. Tarski is all about model theory and truth and falsehood. There's nothing in Gödel's theorem about truth and falsehood. It's about provability. So Tarski's theorem is giving you something roughly like this. It's saying this statement is false in your model theory. And you can go through a similar argument using Gödel numbers again, and end up with an equivalent result, but talking about model theory rather than proof theory. The Tarski statement either has to be both true and false, or it has to be neither. Yeah, it's like saying I am a liar. Every sentence I say is a lie. So Tarski goes down in history as the second most famous logician of all time. like Philosophy Dictionary actually defines him as the second most famous logician of all time. The result is the analog of Gödel's result, but they're like mirror images. There's the proof theory and the model theory. And Gödel's completeness theorem shows that they correspond, because anything provable is true and anything true is provable. Maybe that's a good place to stop, or do you want more? It gets even more fun.
Me in the future, fresh, could do more. With this time traveling theory you have of being able to record this on video, me in the future will probably say yes.
Right. Let's do it for the video then. Okay. Look, I hope you'll all go away and meditate on the truth or falsehood or otherwise of the Gödel statement. Okay. Let's make this even more crazy now. Forget about formal logic, forget about model theory, forget about everything we've learned really, and just look at the Gödel statement as a human being, you know, or look at its English translation if you like, as a human being. This is a statement about some logical system. Okay. Is it actually true, or is it actually false? You know, can this logical system actually provide a proof of it or not?
I think it can, although I don't think that's a good thing.
So most people would say that it can't, because the theorem states that system S cannot prove it. Or the formula, sorry, formula G states that system S can't prove it. So just as a human, let's imagine some possible worlds, right? Let's imagine a world where the sentence is actually true. So imagine system S is your computer. It's running your big AI logic system, trying to prove this thing. So sentence G says system S is unable to prove sentence G. Yeah. Now imagine a world where sentence G is actually true. Yeah, where it's actually the case in the actual world that system S cannot prove sentence G. So what would that world be like? Does it make sense to imagine that world? You know, this is a world where your AI system is chugging away as hard as it can, desperately trying to prove sentence G, but never actually manages to prove it. So is that a coherent possible world that you'd be living in?
I think so.
Yeah? Yeah?
Yeah.
Okay, that sounds pretty coherent, right? Let's consider sentence G is actually true. And the word actual means its philosophical sense of the world we actually live in. Yeah, so this is a coherent view of the world. Okay, sentence G says system S is unable to prove sentence G. And you can easily imagine a world where that is actually true. You can imagine system S is working as hard as it can. You know, the CPU is overheating, the fan's coming on. It's working as hard as it can to prove sentence G, and it is unable to do so. And the fact that it's unable to do so is exactly what is expressed by your interpretation of sentence G. Right? Sentence G says system S cannot prove sentence G, and it can't. Okay? So we can certainly imagine a version of the world where G is true and the system can't prove it, which is exactly what it says on the tin. So, you know, like when you were able to prove that I cannot prove this sentence, you know, you can stand outside of system S and you can see that it is actually true, but system S can't see that it's true. Now, the problem is the completeness theorem, because the completeness theorem says that everything provable is actually true in the model theory, and everything that's true in the model theory is provable. And so This now shows you that there is not only a problem with your proof system, but there is also a problem with your model theory. Because whatever model theory you used along with your proof system is incapable of capturing your human notion of truth and falsity. So this is what is expressed by Tarski's theorem. Tarski's theorem is sometimes written in English as it is impossible to define truth. You cannot give a computable definition of model theory, which always works. If you try to write down an algorithm for saying what is true and what is false, you have the same problem that Gödel has for proofs, that there's always something that can break it. So we now have 3 different properties which we can consider if we're given a formula, and they're all slightly different from each other. We can look at a formula and we can say, is it provable? Is it true in the sense of your model theory? And then you can say, yeah, but is it actually true? I mean, really, actually true. You know, we're now in this even weirder situation where we've got the Gödel sentence G saying system S cannot prove sentence G. And in this world, system S can't prove sentence G, but its model theory can't say that it is true either. So your human definition of truth appears to be something which is distinct from both anything that your computer can prove and also from anything that your computer can consider to be true according to its model theory. So there appears to be something that you, a human being, can do which your computer can never do. You can always give it this Gödel statement and your computer is completely unable to see whether or not it is provable or true, but you can. One way you might try and solve this is by giving your logical system an extra axiom. Okay, the system's got into trouble. There's something that it can't do. The computer system cannot do something. It's going to come and ask you for help. It's going to say, we need a human to sort this out. Only you can make this decision. Is the sentence actually true or not? And you're going to go in and you're going to create a new axiom. You're going to look at it as a human being and you're going to say, yeah, actually system S can't prove G. And I'm just going to tell you that. You know, here's a new axiom. Add this to your set of axioms. And now you can go and prove or disprove G whenever you like, because its proof follows trivially. You just invoke the axiom and you're done. You know, so now you can prove sentence G. You now have a new logical system which has an extra axiom. Let's call this system S star. You've created a new system that is better than the one you started with. And it's better because now it can prove sentence G by invoking that axiom. Yay, we're all done. Yeah, modernism is restored and logic can prove everything again. Or not quite, because we now have a new system called system S star. So what are we going to do now? We're going to create a new Gödel statement about system S star. So the original Gödel statement was about system S. My slides have frozen. One moment. Maybe it's a way of telling me we should stop.
Your slideshow smelt a rabbit hole and gave up.
I've actually confused my computer by talking about this. Oh, here we go.
There you go.
Okay, cool.
It's solved.
Right, we now have a new logical system, S star, that is supposed to be able to do everything. All we're going to do now is come up with a new Gödel statement. Let's call it G star. And G star is going to say system S star cannot prove G star. Okay? So we could do the old sentence, but now we've created a new Gödel sentence for the new system. And the new system is going to have exactly the same problem that the old system had. Because again, if it could prove it, then it couldn't. And if it couldn't, then it could. So, once again, we might go in as a human being and offer to help. The computer is going to say, I can't decide this. The problem is choice. You, human, need to come and make the choice for me. So at this point, we're going to go and add this as another axiom. So now we have added, that's the wrong slide. Now we're going to add this new axiom as well. Now we're going to add an axiom saying system S star can't prove G star. Now we've got a new system called S star star, which can prove G and G star. Now consider the Gödel statement for this sentence. Now we have G star star, which says system S star star cannot prove G star star. And at every point in this process, the system is going to come and call you, human, for help to answer the question that it cannot answer. You're going to make the choice, chuck in a new axiom, and then you're going to confuse it again, and so on and so on. And the precise meaning of "and so on" is explored in Alan Turing's actual thesis. This is not the so-called Church-Turing thesis. This is Turing's actual PhD thesis, which was supervised by Church. It was a problem suggested to him by his supervisor to go and work on. And what Turing actually does is he explores what it means to go on adding this infinite stack of axioms, just chucking in more and more axioms. And you very quickly realize you can start to add whole infinite classes of axioms and then classes of axioms to try and define what is meant by and so on here. If anyone's still following it, there's only 2 slides left. Let's get to the end.
What? I don't see why you can't do the oh. Well, maybe you just answered my question for me. I was about to say I don't see why you couldn't do the opposite and then do something weird.
Is the right question. Good. So yeah, look, the system is completely indifferent to what choice you make. It's coming in asking you to make the choice, right? The problem is choice. So yeah, what would happen if you made the other choice? What would happen if you chose the axiom that says the system can prove sentence G? Okay, so this appears to most people to be extremely offensive, right? We have this intuitive human sense of truth, very much in quotation marks, because we haven't defined it. And the whole point of Tarski's theorem is that you cannot define it. But logically, in terms of formal logic, you could go in and you could include the other axiom. So this is what happens if you do that. Here is a non-standard version of the first one. Okay, here we're going to say system S can prove G. We're going to chuck that in as an axiom. Now remember, at every stage of this process, we get to make a choice. So yeah, some of them we could give the standard one that it can't, and other times we can make a non-standard one. So here's a non-standard version of the second one. System S star can prove G. So logically, this works. There is nothing that goes wrong with the logic because it doesn't conflict with anything there. If it was going to create a contradiction, then the system could have answered it in the first place because it wouldn't be an axiom. The whole point of an axiom is that it's a new piece of information. So the point is system S can't prove G, but you've put in an axiom saying that it can, which seems to be a very strange place indeed. Now, what actually happened, and remember, due to the completeness theorem, everything provable is true and everything true is provable. So you're not only making statements about the provability of G, but you're making statements about its actual truth as well. So, if we do chuck in an axiom like this, it initially seems completely crazy, but it does actually work. And the easiest way to understand why is to think about historically what happened when humans did things like this, okay? Someone once invented an axiom saying for every x, someone invented an axiom saying that there is a number such that x plus 1 equals 0, okay? So, when was this created, roughly? Probably about 3000 BC or something, right? This is the invention of negative numbers. So the basic model theory you had that looked something like this, only with natural numbers, you would have felt in a similar state of confusion to what you're feeling now with these non-standard Gödel sentences. Okay, and then someone decided to include this as an axiom, and then we figured out we could extend this model of arithmetic by creating new numbers, and we called them -1, -2, -3. We created these new numbers and put them in our model theory, and they were able to satisfy this crazy axiom that someone had added. It happened again in ancient Greece when someone decided to create an axiom like this. They said, suppose there is an x such that x times x equals 2. Okay, and this invented irrational numbers because the square root of 2 couldn't be defined through any of the mathematics of the day. So at this point, we had to add a whole bunch of extra numbers to our arithmetic. All these new things somehow linked to the numbers we already had, but representing irrational numbers. It happened more recently when someone decided to add an axiom like this, saying there exists a number x such that x times x equals -1. So this is the square root of -1, which we often write as I. And I is not a natural number, it is a complex number, and you have to extend your model theory with more numbers. So if as a human you make the choice to go this other route, to add any of these non-standard axioms, you end up with a system that still works, but you have to extend your model theory. This is called this is the same symbol as Gödel, right? Leuenheim-Skolem theorem, I think. You can extend your model of the numbers with a bunch of other numbers, which here I've colored red, okay? So as well as having the normal number 1, number 2, number 3, you also have red number 1 and red number 2 and red number 3. And this is a different substance from the original number 1. Just like the number 2i is a different substance from the original number 2. Now this is red 2. And they obey the same kind of laws of arithmetic. Red 2 plus red 3 equals red 5. But red 2 is a different thing from the normal number 2. And red 5 is a different thing from the normal number 5. So if you make the choice to extend your logic in this other way, you will have to create this new set of numbers in the same way that we've created negative numbers and irrationals and imaginary numbers. It's a new class of numbers that has to be added to your model theory. And again, for many people, this is painful because in modernism, it was thought that mathematics is the one true system that describes the world we live in. But what you see now is there's an infinite number of systems of mathematics, and it's up to you as a human being to pick the one you want to be in that is the most useful for the world that you live in. I'm really going to stop there now. There was going to be a workshop, but if you want to work on some of this stuff at home, please have a go at some of these exercises. you can do that proof checking. Take the proof that I gave you on the slide. That comes from the Huth reading I've given you. Convince yourself that it works. Have a little meditate on the meaning of the Gödel sentence and some related sentences. If you enjoy the logic, try some of the other proofs from Huth. Try some of the exercises from Huth. You know, as always, we don't expect you to understand every detail of this. We're trying to give a flavour of where this is all going. But the moral of Gödel's theorem, Tarski's theorem, and the model theory that developed after it is the problem is choice. Sometimes a system gets stuck and it has to come and ask you as a human to make that choice for it. Hope that was fun. Maybe you'll end it more on the recording. There'll be another reading on Blackboard about formal verification for us to talk about next week. Maybe next week there won't be any slides. Maybe we'll just talk literally through the book chapter because I want to follow it pretty closely. It should all get a lot easier from now on. This was the hard bit. We're now going to go and look at applications of all these ideas. Any more questions? Tired?
Help.
Got to go meditate for 5 hours on this.
Yeah. Meditation is recommended at this point.
Wow.
Yeah, no questions from me.
Good. See you all next week. Enjoy.
Yep.